Good day, everyone. So this video covers the discussion on cyclic quadrilateral. Then we have the circles and the geometric figures cut from circle. So we have sector of a circle and segment of a circle. Okay. So by definition, a cyclic quadrilateral is a quadrilateral with all four of its vertices lying on a circumference of the circle. So meaning, this is just a special case where for a quadrilateral, we can draw a circumscribed circle. So if this is the quadrilateral, we can draw a circumscribed circle, meaning all the vertices lie on the circumference of the circle. Okay, so the vertices can be represented by big letters A, B, C, and D, and also this represents the interior angle at the vertices or the vertex angles. And then the sides be represented by small letters A, B, and C. So what are the properties of the cyclic quadrilateral? So, number one, the opposite angles are supplementary. So, meaning, if you have here the angles A and C, if you add, that is equal to 180. So, if you have here the opposite angles B and D, if you add, that is also equal to 180 degrees. Okay, number two, we have here an exterior angle is equal to the measure of the opposite interior angle. So that is, let's say I will draw an exterior angle here. So exterior angle alpha is equal to interior angle A. So exterior angle is equal to the opposite interior angle. So this can be easily shown because the sum of angle C and alpha here is 180. They are supplementary. And the sum of angle A and angle C here is also 180. So meaning, alpha is equal to A. So same if we will draw an exterior angle beta here. So beta is equal to the opposite interior angle B. Then number three, we have the product of the diagonals is equal to the sum of the products of the opposite sides. So the products of the diagonals is equal to the sum of the products of the opposite sides. So if this is diagonal D1 and diagonal D2, so the product D1 times D2 is equal to the sum of the products of the opposite sides, AC plus BD. Okay, then we have the formula for the area of a cyclic quadrilateral, where S is the semi-perimeter. By the way, this formula can be applied if in case you are given the four sides. But even in case you are given another situation, so some interior angles are given, some sides are given, you can just use any other way as long as you can compute the area of the cyclic quadrilateral given. So let's say, for example, you are given two interior angles there. Then you have diagonal and then some of the sides. Maybe not all the sides are given. So of course, we can just divide the quadrilateral into two triangles. And possible, we can use the area of the triangles in order to solve for the parts of the quadrilateral. Then the total area of the quadrilateral is just the sum of the areas of the parts. So if we divide the parts, or if we divide the quadrilateral into two triangles, then the area of the quadrilateral is equal to the sum of the areas of the two triangles. Okay, so that means it is your strategy how to obtain the correct answer for the question. But if in case you are given the four sides only, so I think this is the best way to answer it. Then we have also the circumference of the radius of the circumscribed circle. So we have here R equal to this. So again, This is only if you are given the four sides, no? Compute the area and then solve for the r. But again, if in case you are given some other parts, so possible, you have another way of solving for the radius of the circumscribed circle of the triangle without using this formula. Okay, so sample problem, we have here points A, B, C, and D, and E are on the periphery of the circle. So AB equal to BC equal to CD. So if the value of the angle BAC is 35 degrees, find the angle DEA. So again, when we have geometry, trigonometry problems, no? So worded problems yan lahat, and then we need to read and understand and then draw the figure correctly, no? So we have here points on the periphery or the circumference of the circle. Okay, so start, no? Draw. So you have the circle and then you have points A, B, C, D, and E. 5 points, no? Then stated here, AB equal to BC equal to CD. So let us say, I have here point A, then I can draw AB. Then BC, somewhere here, yung C. Then AB equal to BC, so the same length as AB. So I have here C. CD is also the same length as AB and BC. So possible D is somewhere here. Then DE and EA not mentioned in the problem. So we can just place them anywhere. So you have there the 5 points and then we will connect them by lines. So of course this is not a quadrilateral because we have 5 sides. Okay. So we are given angle BAC. So where is angle BAC? BAC. So we will connect A and C by a line segment, and then this angle BAC is equal to 35 degrees. Okay, requirement. Find the angle DEA. So DEA. This angle here. Okay. So, considering ABC, this is a triangle. And since AB is equal to BC, this is isosceles. So, AB and BC are equal. So, this angle at A and angle at C for triangle ABC are equal also. Can you follow? So, this is 35 degrees. So, 35 plus 35, we have here 35 plus 35, we have 70. So this measures 110. Can you follow? Okay. Now, how will we solve for E? Now, take note that angle C here is also 110. What's your reason? Because this AB and BC, including angle there is 110, we have also BC and CD equal. So AB and BC equal, BC and CD equal. So this is also 110 here. Okay. So if the angle at C is 110 and then this angle here is 35, I can solve for this angle here. So 110 minus 35, this is 75. And as you notice, we can consider quadrilateral ACDE. And quadrilateral ACDE is cyclic, without this triangle. So since this is a cyclic quadrilateral, then the angle 75 and the angle at E, which I represent it by theta, the sum is equal to 180. So we can just consider quadrilateral ACDE, which is a cyclic quadrilateral. So if you sum up, 75 plus theta, that is equal to 180. And theta is equal to 105 degrees. Okay? So that is using the property of the cyclic quadrilateral in which the opposite angles, when you add up, that is equal to 180 degrees. Okay. Problem number 2, we have here, a quadrilateral ABCD is inscribed in a circle having a diameter AD equal to 8.224 centimeters. If AB equal to 2, BC equals 4, and CD equals 6, find the area of the quadrilateral. Okay. So, this is a cyclic quadrilateral na. So, inscribed in a circle. Quadrilateral is inscribed in a circle. Then, what are the measurements of the sides? We are given AB is 2, BC is 4, CD is 6, and AD is 8.224. Okay? So, the question is the area of the quadrilateral. So, of course, we are given the 4 sides, so we can use the formula na for the area. So, solve for the semi-perimeter S equal to A plus B plus C plus D over 2. So, we have all these sides there. So, S is 10.112. Then we can solve the area using this formula. So, substituting values, we come up with 19.62 square centimeters. Okay? So, that is direct use of the area of the cyclic quadrilateral. Next, we have here general quadrilateral. Na? So, when you say general quadrilateral, that is any form of quadrilateral not mentioned in the preceding videos that we have. Na? So, it is not a parallelogram, it is not a rhombus, it is not a trapezoid, it is not a rectangle, or whatsoever special cases that we have. Na? So, general quadrilateral. Na? Okay, so with unequal sides, and with unequal angles. Okay, so let us say we have here a quadrilateral, then we have the angles, interior angles, same, then we have the sides, small letters, the diagonals D1 and D2, then we have here alpha, which is the angle between the diagonals. So, the area of the quadrilateral can be solved by using area is equal to 1/2 D1 times D2 sine of alpha. So, this formula of the area expresses, or the area here is expressed in terms of the diagonals and the angle between them. Now, if you observe, diba we have presented this formula already. Area is equal to 1/2 D1 D2 sine of alpha. So, as we noticed here, this is not limited only for parallelogram, for rhombus, diba? So, this is applicable to any quadrilateral in which you know the diagonals and the angle between the diagonals. So, if in case we are given a diagonal, we are given a quadrilateral, known yung 2 diagonals and the angle between 2 diagonals, then we can just use this formula to solve for the area of the quadrilateral. So, here, given 4 sides and sum of opposite angles. So, if in case, known yung 4 sides, small letters A, B, C, and D, and then the sum of 2 opposite angles. So, the sum of 2 opposite angles. Okay. So, let's say A and C are known, or if not known, the sum is known. Then B and D known, or if not, the sum of the 2 is known. So, we can solve for the angle phi. And the angle phi is half of the sum of the opposite angles. Then the area of the quadrilateral can be solved using this. Okay? So, we have that formula. Okay? So, sample problem we have here. Find each interior angle measure of a quadrilateral. If its interior angles are represented by x plus 10, 2x plus 10, 3x minus 50, and 2x minus 20. So, solution, we can draw a quadrilateral and let us say this is the first angle represented by x plus 10. The second angle represented by 2x plus 20, the third, and then we have the fourth. So, what are the measures of each angle here? No? Okay. So, for a quadrilateral, we know that the sum of the four angles is equal to 360. No? So that is, or we can compute it from the sum of the interior angles, n minus 2 times 180. So n is the number of sides. So if we have 4, then the sum of the interior angles is 360 degrees. Okay, so applying that, so we can sum up the 4 and then equate to 360. Na? And from this, we can easily solve for x. That is 50 degrees. So if x is 50, so we can now solve for the first angle. This is 16. This is 120. This is 100. And this is 80. So the four angles are 60, 120, 100, and 80 degrees. Okay? Next, we have a quadrilateral has sides A equal to 12, B equal to 18, C equal to 20, and D equal to 22.12. The sum of two opposite angles is 170 degrees. Find the area of the quadrilateral. Okay. So, for this quadrilateral, we are given the four sides, no? And then we have also the sum of the opposite angles. So, I will just represent the opposite angles by A and C, no? Then we are asked for the area of the quadrilateral. So, as we have discussed earlier in the previous slide, that if in case we are given this situation for the quadrilateral, then we have a formula to be used for the computation of the area. Okay. So, I will compute for the angle P, that is half of the sum of the opposite angles. No? So, that is 85. So, 70, the sum of the two opposite angles is 170. So, phi is equal to 85. Then I will just use the formula. So, solve for the semi-perimeter, then apply the formula for the area. So, kindly substitute now. I have computed S, then A, B, C, and D are already given. Angle phi is given. Then press calculator, that is 310.73. Okay, so that is about the remaining topics for quadrilaterals. Now, so we have the cyclic quadrilaterals and then the general quadrilateral. Next, we have circle, segments, and sectors. Okay, so a circle is a set of points in a plane that is equidistant from a fixed point called the center. So, if this is a circle, then we have here the center. And the circle is composed of points, many points. And each point has a distance of r, which is called the radius from the center. So we have here the chord. Then we have here the diameter. And then we have here the second. So we have the tangent. And then we have the point of tangency. Okay, so a sector of a circle is a plane figure bounded by two radii of a circle and an arc. So the figure below shows a sector. So this is bounded by two radii and an arc. So we have here the formula for the area. By the way, we have a bigger sector here. So this is a smaller sector in which angle theta is smaller than 180. And for the bigger sector here, the angle theta is greater than 180. Okay. So area of the sector is equal to 1/2 r squared theta. And the length of the arc S is equal. So we will apply now. So by the way, in the above formulas, the angle theta is in the radian unit. So, problem number 1. Circles A, B, and C are tangent externally and each radius is equal to 3 inches. Find the total area of 3 circles plus the curvilinear triangle formed by the 3 circles. Okay, so we have 3 circles, A, B, and C. They are tangent externally to each other. They have equal radii, 3 inches. Then we are asked to find the area of the 3 circles plus the curvilinear triangle formed by the 3 circles. So what do you mean by the curvilinear triangle formed by the 3 circles? Okay, so let's draw the figure now so that we can view it. Okay, so triangle 1, triangle 2, triangle 3, A, B, and C, as indicated in the problem. So each has a radius of 3 inches. So find the area of the 3 triangles. And then as you notice here, this is what it means by the curvilinear triangle formed by the 3 circles. So that is the area in between the 3 circles. So we have this area. Okay? So 3 circles plus this area. So siguro our strategy, our approach in solving the problem is to solve for the area of the 3 circles and then times 3, and then we will solve for this area. So that we can add. But here, in my solution, I will just slice this triangle indicated in the figure. So this is an equilateral triangle with the sides is equal to 3. Then I will solve for the area of this triangle, and then notice that I have also a sector of a circle here. So circle without this part of the triangle. So the solution now for this question is I will solve for the area of one sector and then multiply it by 3. And then I will add the area of the triangle. This triangle which is equilateral. So that is now the total area here. Okay, so I will solve for the area of the triangle. 1/2 6 squared sine of 60. So that is 9 square root of 3. Then I will solve for the area of the sector without this triangle, without this part here. So here. So if this is 60 degrees, so the interior angle, so I have a bigger sector. So I have a bigger sector need to be solved. Then the central angle is 300 degrees. The radius is 3. So from the formula, area is equal to 1/2 r squared of theta, where theta is in radian unit. So 1/2 3 squared times 300 times pi over 180. So that is 15 pi over 2. So the area total is equal to area of the triangle plus twice the area of the sector. That is equal to this value. Okay, next problem we have here. Find the radius of a circle if an arc of length 2 pi has a sector of area 10 pi. So find the radius of a circle if an arc of length 2 pi has a sector of area 10 pi. So let's draw the figure, So that is a sector of a circle. So the length of the arc is 2 pi and the area of the sector is 10 pi. Find the radius. So from the formula, area is equal to 1/2 r squared theta. So the area is 10 pi. Okay, now I can separate the right side. I will write it as 1/2 r and then times r theta. But we know this value r theta is equal to the length of the arc. Can you follow? So r theta is the length of the arc. So we are given the problem. In the problem, area is 10 pi. And then the length of the arc is 2 pi. Then what is the radius? So we can substitute, no? So area is 10 pi. The length of the arc is 2 pi. So we can solve for the radius, and that is equal to 10. So that is about sector of a circle. Okay. What is a segment of a circle? So a segment of a circle is a plane figure bounded by an arc of a circle and the chord of the arc. Ano? So bounded by an arc and the chord of the arc. So we have here our figure. So from a circle, we cut a portion containing a chord and the arc of the chord. Okay. So we have here a segment of a circle. So the radius of the circle is r, and then we have here the central angle theta. I can also slice, or the small area where theta is less than 180, that is equal to 1/2 r squared theta minus sine theta. Okay. By the way, this formula, it can be easily memorized if you know where we derive it. Now, simply, this is area of the sector minus area of this triangle. So we have here a sector. This is the shaded portion is called a segment. But if you consider r and the angle theta and the arc, this is a sector. And the area of the sector is 1/2 r squared theta. And then, this triangle, the area can be solved, which is equal to 1/2 r squared sine theta. So if you subtract and then factor out 1/2 r squared, then we come up this formula. So in this formula, the angle theta here in the first is in radian, because 1/2 r squared theta is the area of the sector, where the angle theta is in radian. But when we press the calculator by the sign of angle theta, so this angle theta is in degrees if our calculator is set to the degree mode. Okay? So take note of that, so that you can come up with the correct value when you press it in the calculator. So again, the first angle theta here is the angle for the computation of the area of the sector, and that is in the radian unit. But here, this is for the computation of the area of the triangle, so it depends on the mode of the calculator. So usually, our calculator is in the degree mode, so the sign of this angle theta, so theta should be in the degree unit. Okay. How about if you compute for the area of the bigger segment? So let us say this segment, you will solve it. So in our figure, the angle theta is here, and then I will represent this by angle phi. So observe that area now of the bigger segment where angle phi is greater than 180 is now equal to this. And how we come up this formula? So that is, we compute for the area of the big sector. We compute for the area of the big sector where the central angle is phi. And then we add the area of this triangle where the central angle is theta. So 1/2 r squared phi is for the area of the sector. So meaning angle phi should be in the radian unit. Plus 1/2 r squared sine theta is the area of the triangle. So when you press sine theta, if the mode of the calculator is in degrees, so this angle theta should be in the degree unit. Okay? So problem. Find the area of a segment if its central angle measures 60 degrees and the radius of the circle is 12. So we can draw the figure. I think this is very simple. So this is direct substitution to the formula. Radius r equal to 12, central angle is 60, and then find the area of the segment. Okay, so this refers to the small segment. So we can use the formula. Area equal to 1/2 r squared theta minus sine theta. So the first angle theta should be in the radian. So express 60 degrees in radian. Then minus sine of 60. So we come up with this answer. Okay, so possible we encounter problems involving both sector, segment, circles, relations so we will just combine all the formulas that we have triangles, sectors, segments in order to solve for the requirement so just draw the figure correctly and then observe analyze how will you solve the problem. I have here problem 2. The length of the common chord of two circles intersecting each other is 48 centimeters long. The distance between their centers is 17 centimeters, and the radius of one circle is 25 centimeters. Compute the diameter of the second circle. So we have here the length of the common chord of two circles intersecting each other. So, solution. We have two circles, intersecting each other. So, let's say this is circle 1, and then we have here circle 2. So, the length of the common chord. So, this common chord, is 48. So, the length of the common chord is 48. And the distance between their centers is 17. So, meaning if I will connect their centers by a line segment, the length there is 17. And the radius of one circle is 25. I think this is the smaller one. By the way, since this is 48, so this is being bisected by the line connecting their centers. So we have here 24. The radius of the smaller one is 25. So we have here 24, 24. I can solve for this value here. I will call it x. I will consider this triangle. So I have x squared equal to 25 squared minus 24 squared. And that is equal to 7. So the question is to solve for the diameter of the second circle. Okay, so I will start with the radius. Okay. So for the second circle, this is the radius r. And since this is 17, and then we have here 7, so this remaining distance is 10. I can also consider this triangle from the red circle. So I have here r squared is equal to 24 squared plus 10 squared equal to 26. Therefore, the diameter is equal to 2r. And this is equal to 52 centimeters. Okay. So, problem 3. ABO is a circular sector having a central angle of 30 degrees with O as the center. If point M is located midway between OB, determine the area of ABM if the radius of the circle is 4 cm. Okay, drawing na naman, So again, read and then draw the figure. Okay. ABO is a sector having central angle of 30 degrees. So ABO is a sector having central angle of 30 degrees. O as the center of the circle. Okay, so this is the arc AB. This is 30 degrees here. Okay. M is located midway between OB. So M is located midway between OB. Determine the area ABM if the radius of the circle is 4. Meaning, we will connect a line segment from A to M. Then the radius of the circle is 4. So this is midway. So we have 2. Find the area ABM. That area there. Okay, so how will we solve it? So observe that area ABM, which is shaded in green, is simply equal to the area of the sector minus this area of the triangle. Then we have there all the values. So, angle theta, radius r, then this is 2 for the triangle. We can also solve it. So, isa-isahin lang natin, ha? So, area 1 is the area of the sector OAD. So, formula, 1/2 r squared theta. So, substituting values, we have 4.19. Then, I will call area to, area of triangle AO or AMO. Huh? So, 1/2 times 2 times 4 sine of 30. Then, this green area is the difference between the two. Okay, so 2.19. Okay lang? Problem 4. Two perpendicular chords, both 5 centimeters from the center of the circle, divides the circle into 4 parts. No? Okay? Two perpendicular chords, both 5 centimeters from the center of the circle, which divides it. Kindly place it. No, which divides it into 4 parts. Meaning, the circle is divided into 4 parts by the two perpendicular chords. So, if the radius of the circle is 13 centimeters, find the area of the smallest part. Okay lang part? So, find the area of the smallest part. Okay. So, let us draw. We have a circle. Then, I will draw two perpendicular chords to the circle. So, I have there. So, each chord measures 5 centimeters from the center of the circle. Then, the circle now is divided into 4 parts. Find the area of the smallest part. Okay, so find the area of the smallest part. So that is area shaded in green. So what is our approach in solving the problem? What should be our flow of the solution? Okay, so I will label the important points here by letters. The center at O, and I will call this point A, call this point B. So if I will connect A and O, this is the radius of the circle, and that is 13. Notice that if I will connect also OB, that is another radius, and I have formed sector ABO. So sector ABO. Now, notice, this is a triangle here. This is also a triangle. And the two triangles are the same. They have equal areas. So, I can easily solve for the area of the smallest part, that is the area shaded in green, by using the area of the sector minus twice the area of the triangle. So, the problem there is, are the data available for all data needed for the computation of the area of the sector and the area of the triangle are given. So, for the sector, radius, and then we need central angle. Not given. For the triangle, we have many ways of solving it. It can be 3 sides or 2 sides and 1 angle. Okay. So, we will check each. Okay. So, but that is our flow. So, solve for the area of the sector, then subtract twice area of the triangle. Okay. So, I will have here point C. Then, I have formed here a triangle. So, this is 5. This is 13. I will call this angle beta. So, consider triangle ACO. I can solve for beta. So, beta, I will use sine. Sine of beta is 5 over 13. That is 22.32. Okay, now, if this is angle theta, notice that this angle here is equal to 45 degrees. Why 45? Because we have here 5 and then we have here also 5. So isosceles right triangle, so this is angle 45. So to compute for angle theta, have you noticed that angle theta is equal to, this is half of theta na? This angle is half of theta. So notice that half of theta is 45 minus beta. So the angle theta is simply equal to twice of the difference 45 minus beta. So I have already beta. So angle theta is 44.76. So observe that we can now solve for the area of the sector because that is 1/2 r squared times the angle theta. How about this triangle? How will we solve it? Okay. So I will go back to triangle ACO. This is 5. AO is 13, the radius. I will solve for OC, distance OC, by using Pythagorean theorem. So I will call the distance OC equal to x. So x squared is equal to 13 squared minus 5 squared, and that is equal to 12. So if this is 12 and this is 5, so meaning this is 7. No? And if this is 7, this is also 7. And then I will call this point B. So have you noticed that if we know it, we have now the side AD, which is 7 of the triangle, and then we have this 5, and notice this distance 5 is the altitude of the triangle. Altitude to side AD. So I can now compute for the area of the triangle because we have area of the triangle is equal to 1/2 the product of the base times the altitude. Okay, so I will compute now. Smallest part is equal to area of sector ADO minus twice area of triangle ADO. So area of sector is 1/2 r squared theta. Then area of the triangle 1/2 7 times 5. Multiply by 2. Then we have the area of the smallest part. 31 square centimeters. Okay, so that presents the problems involving cyclic quadrilateral, general quadrilateral, and then for circles and the parts or the geometric figures cut from circles, we have the sector and the segment. Okay, so stay tuned for the next videos to be posted. Thank you for viewing my video, and I hope this is helpful in your review or the understanding of the topic. Thank you very much.